Okay, good afternoon, everyone. Hi, USask. My name is Gwen Grenier. I'm a professor at the University of Regina, and I'm also the national coordinator for the 2024 CAP lecture tour. Before we get started, just a couple of announcements about how the talk will proceed. All of the questions will be handled at the conclusion of the speaker's presentation and will alternate between questions from those attending in person and those participating virtually. For those attending virtually, post your questions in the virtual chat on Zoom at any time, and your questions will be posed anonymously to the speaker by the MC. For those attending in person, please wait until you're called on to ask a question and then use the microphone provided to ensure that those participating virtually can hear you. All students participating today, both online and in person, are encouraged to remain after the talk and participate in a 15 to 20-minute informal discussion session with the speaker. We also invite any faculty or other attendees at USask to participate as well. So with that, it gives me great pleasure to introduce our host for today's CAP lecture tour talk, Prof. Sasha Kustov of Physics and Engineering Physics Department at the University of Saskatchewan, who will introduce our speaker and get today's session started.
Okay, so welcome everyone to sixth and final talk of the CAP, Canadian Association of Physicists lecture tour series for 2024. As already said, I'm Sasha Kustov, and I'm pleased to host this talk from the Department of Physics and Engineering Physics at the University of Saskatchewan. We welcome the audience that is participating both in person here and at the university, and those who are joining us virtually. This event is being recorded to be made available for later viewing at the CAP YouTube channel. So first, as we gather here today, we acknowledge we are on a Treaty 6 territory and a homeland of the Métis. We pay our respect to the First Nations and Métis ancestors of this place and reaffirm our friendship with one another. The CAP the lecture tour series is sponsored by the CAP Foundation and by the CAP, which is again Canadian Association of Physicists, a national network of about 1,700 physicists working at the universities, companies, and research institutions across Canada. The CAP works hard on behalf of Canadian physicists to support physics education and research and sponsors a number of physics activities, including this lecture tour and national research conferences. CAP delivers a number of programs for undergraduate and graduate students, research conferences, physics scholarships and prizes, and it has a student advisory council. If you have not already joined the CAP, please consider becoming a part of Canada's largest network of physicists and physics students. It's free for undergraduate students and for the first year of membership for graduate students. So today's talk is about 45 minutes, followed by 10 minutes of questions. If you would like to pose those questions to the speaker, you can type your question on the chat at any time, and I will ask the question on your behalf at the end of the talk. Following the talk today, all participating students plus faculty or other members of the host department will have the option to remain for an additional 15-20 minutes to speak directly with the speaker and ask additional questions about the research or about the related career path. Priority will be given to those students who are attending virtually, as those attending in person will have a chance to interact with the speaker at the close of the event as well. And now, it's a great pleasure for me to introduce today's speaker, Professor Jason Holt of the TRIUMF. Professor Holt's research focuses on the interplay of atomic, nuclear, particle, and astrophysics to elucidate the mysteries of the universe, while also passionately bringing the gap between Science and Art in Public Outreach. Today, Professor Holt will present his talk entitled The Atomic Nucleus as a Window to the New Physics. Welcome, Professor Holt.
Right, I will take it from here, I suppose. Hear me? This is all good? Fantastic. Now, let's do a little screen sharing. Let's go for it. This all looks good? No, that's okay. I'm getting the wrong version here. There we go. Fantastic. All right. Cool. I think we're good. Okay. Thank you for coming and putting up with whatever that was. So it's fantastic to be here. And so I would just like to share a little bit of a story with you today. And this is, oh, there we go. And let me make sure this goes. Yes, okay. So this is a story, as you can see, this of a revolution that is taking place in our field of nuclear theory. So, and it's a revolution not just in how we understand the atomic nucleus, but all of the exciting new physics that's connected with it. We'll be talking about all of this. And so, let's see. Right, so what you'll see is that we're at a point where we're not just able to describe and calculate properties of the nucleus from the light to the heavy systems, even potentially connecting to neutron stars, but we'll be able to do this from first principles. And so what this means is that the atomic nucleus no longer will be this tremendous obstacle that's, obscuring new pathways towards discovering new physics, but rather a window where these paths are quite clear. So whether we will talk about discoveries of new properties of neutrinos, or the existence of dark matter, or the cosmic origins of the elements, or even violations of fundamental symmetries, which could explain why we exist, they're all part of this story. And I'm glad there's so many of you here and out there in Zoom land who are here to hear about this story, because I know what you probably think of nuclear physics. If anything, might just be a complete blank of static. But if you do have some perspective, it's probably the one that you see in textbooks and with pictures that look like this. And it goes on, and all of these different models, whether it's about mean field or boson models, you have all of these different models. And you would not be to blame if your perception was some linear combination of all of this. And I hope that for many of you, or for at least a good number of you, that this is your perception, because by the end, I'm pretty confident that this will change. Because as you might guess, this is absolutely not what I do. And we want to start thinking in a new direction in the field. And so why is that? Well, there's two key reasons that I'll discuss today. Exhibit A, isotope production. So there's not so many nuclear physicists here, but so you may not know that as of last year, we have truly entered an unprecedented era in nuclear science. So with the advent of what we call the Facility for Rare Isotope Beams that's been come online in the United States, it's over $1 billion expenditure. So with this facility, hundreds, if not thousands of new isotopes will be produced and studied in the laboratory. And it's up to us as a community to decide how we can maximize this unique opportunity. And for me, this is pretty easy. I'm a theorist, so it is to maximize the meaningful interaction with theory. Because sort of as a community, it's easy to fall into this sort of stamp collecting mentality where we're just going to measure the next nucleus because it's the next one to measure. But with billions being invested worldwide, not just in the US and Canada, we want to make sure that we're attacking the most fundamental and the most exciting questions as soon as possible. And it's often theory which drives these questions. Because if we're not doing that, in 10, 20 years, we might be stuck with something that not so many people are going to be interested in collecting anymore. And so the real question is not whether is theory ready. I think we should be asking, is theory ready to lead? And so how could we possibly do that? Well, if we think of what's required of theory, not just in nuclei, but in any field, it's really two simple things. One, we want theory to be able to motivate. We want theory to be able to motivate new, exciting experiments and new, exciting discoveries reliably. And so what that means is if we make a prediction, we want to be able to quantify the uncertainties in some way. So if we tell FRIB there's some exciting new physics out there, let's go measure it, we want to have some confidence that we'll find it when we get there. So we really want to be able to do that. And step two is interpretation. So I think theory really needs, in order to lead, to move away from this model-dependent picture of nuclear physics that I just showed you, and connect, insofar as we can, these beautiful new measurements that will be taking place in these laboratories worldwide, previous page, to the fundamental forces of nature. And as you'll see by the time we get to the end, that this is something that we can now do. But this is just on sort of the nuclear structure side. What's even more exciting to me in this field is how theory can lead in discoveries of beyond standard model physics. And so if you go to your Canadian subatomic physics long-range plan, I'm sure there's probably one under every chair. If you look there, we identify 8 key science drivers that will really be moving Canada forward towards new discoveries over the next decade or more. And if you zoom in on this, you see that for no less than 6 of them is the atomic nucleus a key component, which means reliable nuclear theory is also a key component. So I'll be talking about all of these a little bit at the end if there's time. But what I really want to focus on as kind of a thread throughout this talk is on discovering new properties of neutrinos. And this takes us to exhibit B2. And that is through this process of what we call neutrinoless double beta decay. So I'll talk a little bit more about this, but it's a worldwide search. It's sort of a similar idea to searches for dark matter in these deep underground laboratories. We're searching for something invisible. But if we discover it, it's a tremendous advance in our knowledge of subatomic physics. And in a similar way, theory is also required for motivation. We want to make sure that we are using the best isotopes that give us the best chance for discovering new physics, and also interpretation. We need a reliable theory to interpret if there is a discovery or the current limits on these searches in terms of beyond standard model physics. And so that's what we really need. And this is so important that the United States, the joint funding agencies, DOE and NSF, in their long-range plan, identified constructing next-generation neutrinos double beta decay experiments as the top science recommendation in nuclear science. So that's the level of what we're after. So now, what is neutrinoless double beta decay? Well, yeah, okay. Before we get to all this, I understand there's probably, since many students here and online, who might not even know what regular beta decay is or know much about nuclei. So let me just take a quick step back and just give you a brief tour of nuclei. Okay. So this is how we represent nuclei in the field. So we increase proton number in this direction. So we start with helium, nickel, and all the way up. And for a given element, we can have any number of neutrons. So these are different isotopes that a given element can have. And so the first thing that you should notice about this is it doesn't go on infinity in all directions. There is a limit to nuclei. And so this is what we call the nuclear drip line. So limits of existence, so in terms of removing neutrons or in terms of adding neutrons. And so on this side of the chart, it's actually pretty well pinned down because Coulomb starts to take over and things are much easier to deal with. But on the neutron-rich side, this is really not well known. And it's one of these flagship scientific motivations for these next generation rare isotope beam facilities to really pin this down between, say, oxygen and calcium or even above. So the last thing to notice, also, yes, there are these pillars that you might see where we have oxygen labeled, calcium. These are what we call magic numbers in nucleus. So this is when you essentially have filled nuclear shells. They arise for much more complicated reasons than, say, atomic shells, but it's the same idea. So when you fill a shell, you can have either filled protons or filled neutrons, and it's either singly magic or doubly magic. And so these are sort of the key nuclei that really kind of are the pillars of nuclear structure across the chart. So oxygen 16, calcium 40, all the way up to lead 208, but we'll probably never be able to get there. It's too heavy. And the last thing is to notice is that you have all these black dots sort of in the center. So out of the thousands of nuclei, these represent the few hundred that, as far as we know, live forever. So they're stable. But every other nucleus decays. And why do they decay? Well, life is follow the money, and in physics, it's follow the energy, right? So they decay to a more energetically favorable configuration. So whether we're on this side, we're going to decay towards something more stable here. And if we're on this side, we'll decay to something more stable here. And so then the question is, how do nuclei decay? Well, the nucleus is one of these fascinating objects in the quantum universe because it's where really all the fundamental forces are at play. And each of the three sort of subatomic ones, not gravity, play a role in a particular decay. So here, of course, your 4 fundamental forces in the obligatory XQCD comic. But here's how we kind of can think of the different types of decays. One mediated, the strong interaction sort of mediates what we call alpha decay. The electromagnetic interaction mediates what we call gamma decay. But what I would really like to focus on here is beta decay. And so this is mediated by the weak interactions. The weak interaction is still one of these things that's a bit of a puzzle in some ways. And so what is beta decay? Well, it's simply when you have a neutron decaying into a proton and giving off an electron and an associated antineutrino. So what's the simplest beta decay that we can think of? Well, if you just have a neutron that's just sitting there and you're watching it, drinking your coffee, after 10, 15 minutes, it will change into a proton and giving off, again, the electron and the antineutrino. And so this typically happens in 15 minutes. And there's this fundamental coupling in the universe here, which we call GA. And this tells you how the weak interaction couples to a nucleon. So the size of GA sort of tells you about how quickly or slowly this decay would happen. And GA is an incredibly important quantity in the field. It's something that's fundamental, and it's so important that there are Nature papers written about it. So this was from 2018 or so, where there's this essentially quasi-exact calculation on the lattice of GA. So that tells you essentially how important this quantity is. So keep this in mind, because we'll be coming back to GA in a little bit. So what other ways can nuclei decay? So things can get more complicated when you actually have a nucleus rather than a neutron. And so we can have many types of beta decays. In fact, it's the most ubiquitous form of decay across the chart. So you can, if you're on sort of this side of the valley, you will turn a neutron into a proton. So you're essentially going this way. And since we give off an electron, we call this beta minus decay. You can have the other process on this side. You can have now a proton changing into a neutron and giving off a positron, and this is what we call beta plus decay. So, okay, cool. But now if you look, the lifetimes are no longer 15 minutes. They're 10 to the minus 15 seconds to more than the age of the universe. So now there's no obvious way to handle how long these decays are because they're governed by nuclear physics. They're governed by a nuclear structure quantity, which we call the matrix element. So if you haven't had quantum mechanics before, here you go. It's just one little line of quantum mechanics. So this is your initial nucleus, how we represent it. This is your final. And this is the operator that mediates this decay. So tau basically says you change a neutron into a proton, and sigma says you flip its spin. So that's change a proton to a neutron, you flip its spin. This is what we call gamma of Teller decay. So this is something where if you have this matrix element here, it's directly related to the half-life. You just square this guy. And so it goes both ways. If you can measure this, you know the matrix element. If you can calculate the matrix element, then you can predict the rate. So, okay. Turns out, this is where the plot starts to thicken a bit. It turns out that there is a long-standing problem with gamma of Teller decays. And in fact, it's so long-standing of a problem. If you look at papers in the 70s, they say it's a long-standing problem. So what's the problem? If you try to calculate it, you simply do not get the right answer. And this is typically within these different types of models. So experimental values are always systematically smaller. So what we saw was, well, our theory calculations are too big by, say, 0.7, 0.8. So let's just multiply by that, and we're good. Well, okay, it's 2024. We don't really want physics to be fudge factors. So the question is, can we reevaluate this super long-standing question in the more modern framework that I'm discussing? Where things get more interesting is when you consider, which I've sort of just alluded to it, that neutrinos are produced in beta decays. So that makes the nucleus actually one of the key laboratories where we can really precisely study neutrino properties in principle. And of course, we know that the neutrino is one of the most elusive particles in the subatomic world. We don't know everything about it. We only know a few things, right? Primarily because of some amazing experiments that were done here in Canada and in Japan, where through 2 complementary experiments, we discovered that neutrinos undergo oscillations, which means as they fly through space, they change from one type to another. And that can only happen if they have some non-zero mass. So what we learned from these experiments are two things: that there is a small mass splitting here, this is 2 minus 5 if you can't see, between mass states 1 and 2. So that means there's a small spacing between 1 and 2. What we also know is that there's a larger spacing between masses 3 and 2. But this comes with an absolute value sign. So we don't know the sign of that. So 3 could be larger than 2, or 2 could be larger than 2. And so this is what we refer to as the normal and the inverted hierarchy of neutrino masses. And we don't know which one is necessarily manifested in nature. And the only other thing we know, or another thing that we don't know, is the absolute mass scale of neutrinos. We don't know what their absolute mass is. We only know these mass splittings. So now we can start to think of potentially using beta decays to get at that. Because if we know very precisely the energy of an initial and a final nucleus, and we were to measure this energy spectrum, because the neutrino carries away some unknown amount of energy. And so we have a spectrum like this. And if we had a detector that's so good and we zoomed in at the very endpoint of this spectrum, the actual endpoint would be the energy difference between the two initial and final minus the mass of the neutrino. So in principle, this lets us get at the mass of the neutrino. But it's a long process, and there's experiments being done worldwide, and this one is particularly quite famous. See it going through a traumatized German town there. So whenever I give talks, I like to be very, very thorough. Okay, so we want to think if there are other types of beta decays that we could consider. And I really wish I were clever enough to have come up with this, but this credit here has to go to Andrew from Microsoft, because you can think, right, beta products, right? At a certain point, they will decay into something stable. Like, he came up with a whole thing here. So, but he does qualify the statement by saying that I am pretty sure that the term beta in software isn't related to atomic decays. I mean, yes, same here. I agree with that. But he really put some thought into this, right? Because you start with the garbage here, and then he conserves some Microsoft quantity. I don't know, plus minus here. You get some speed up. You lose bugs, and I put in quotation marks very stable because PowerPoint did only crash 3 times when I was putting this together, so it's all good. But here you have it, and he even goes so far as to give a lifetime for this. So props to Andrew. If you do have any further comments on this or thoughts, please let him know, because this blog so far has 0 comments. So please help him out there. But now we can start to think of other types of beta decays. And so these now we start to get more rare. But if you look across the nuclear chart, some things can happen in peculiar ways. So if you look at germanium 76, he would love to decay to arsenic 76, but it's energetically forbidden. So he only has one pathway open, and that is through what we call a double beta decay. So this is not forbidden or anything in the standard model. So it's just a second order weak process, and it's been measured, but only in really a handful. Again, there's thousands of nuclei, and only really 10 or so. But what it is, it's just essentially two neutrons changing to 2 protons and giving off the electrons and antineutrinos. And so again, this is some sort of energy spectrum, which you can observe like this. And similar to single beta decays, there's a matrix element that governs this, and you can directly relate the matrix element to the lifetime of this. This is just something that's easy to calculate phase-based there. And they all have lifetimes on the order of 10 to the 20 years. So again, just to put that into perspective, that is the age of the universe squared. So tremendously long lifetime. It's the longest lived process that we know of so far. But things get more interesting if the neutrino is its own antiparticle, what we call a Majorana particle. We don't know this. It's a neutral lepton, so it could be. But if it is, then we could have an even more rare process where the 2 neutrinos that are emitted essentially annihilate each other or reabsorbed, or depending on how you want to think about this. And only the 2 electrons are given up. So that means when you're detecting it, you detect just the 2 electrons, and they come out at exactly the energy difference between your initial and final nucleus. If this is ever seen, it is a laundry list of new physics. First of all, it tells us that lepton number is violated in nature. There's been no other examples of that. What that means is you're creating matter with no antimatter. So this could play a role in understanding the matter-antimatter asymmetry in the universe. It tells us the character of the neutrino. And if there's no weird heavy neutrinos going on mediating this exchange, which there could be, But if there aren't, then we can relate the rate of this decay, the lifetime, to this quantity. And so this is a beyond standard model physics quantity. We call it the effective neutrino mass. It's a little complicated. It just comes with some linear combination of neutrinos, so don't worry too much about it. But in some ways, this could help us pin down the absolute mass scale of the neutrino. So this would be amazing, except this guy. Remember before, we had a lifetime, we could get the matrix element and vice versa. But now we're after this guy. We're after beyond standard model physics. And there's no way to get at this matrix element. So this is something, again, governed by nuclear structure and can only be calculated within nuclear theory. And when you go and look at these experiments, as they continue to increase the lower lifetime for this process, you get plots like this. So these are all the different elements that they're using for these experiments. And as they continue to not see anything, you rule out regions of this effective neutrino mass phase space. And so what you see is we haven't even necessarily begun to probe the inverted hierarchy, but perhaps with next generation experiments, we could. Except when you see typically bands like this, when I was naive and I didn't know, I would see an experiment, it comes with a band, I assume that this is an experimental uncertainty, but this uncertainty comes from our lack of knowledge of this matrix element. So this becomes important because this is, as of several years ago, the span of these matrix elements. And so you can see, depending on the isotope you're looking at, it can be a factor of 3, it can be a factor of a little bit more. But when you start thinking about how these were calculated, those all in terms of these different models. And one thing we know is that all models are missing some essential physics. And they like to argue between each other about who's missing what, but they're both missing something. And as you'll see when I get to a little bit later in the talk, something was discovered just a few years ago, which none of these take into account. So you want your theory to be able to reliably, in some sense, give uncertainties. Otherwise, it's difficult to assign much meaning to these numbers. But you could look at this and say, okay, fine, it's a factor of 3, right? Life could be worse, right? We're not on a log plot, so it could be worse. Well, actually, when you realize that this matrix element is squared, you actually are on a log plot now. When you get to the relevant quantity, which is the half-life, the lifetime for this, which is what the next generation experiments need to understand in order to strategically plan. And so if we're talking now about an order of magnitude, so for these experiments, an order of magnitude difference in this quantity will mean either an order of magnitude more time or an order of magnitude more material searching for this. But what it really comes down to is an order of magnitude more money, right? Okay, maybe in physics you follow the money too. So this is tremendously important to be able to pin down this matrix element from reliable nuclear theory. And so what if I told you that we could potentially, we have the capability to maybe go from a plot that looks like this to something like this? Because this is this theory that I've been talking about, but haven't really said anything about. And so this is what we call ab initio, or first principles nuclear theory. And this is the calculation of just say the ground state energies of the oxygen isotopes. But there's no information that went into this beyond information from 2, 3, and maybe 4 body data, which we need to understand the nuclear forces. But from there, these are pure predictions. And we see that all different approaches, who cares about what these mean, agree with each other essentially within uncertainties. And this is a sort of picture that we need for this. And so I always like to say this, whether we're talking about double beta decay experiments or rare isotope beam experiments, we're really entering next generation here. So why not think the same way in terms of theory? And so this is what we're after. And it's in principle, it's very easy to understand what we're after. And so it was laid out beautifully by Maria Goeppert-Mayer in her Nobel Prize acceptance speech. And so here she says that the basic approach, which is what we're after, is to study the elementary particles, their properties, and mutual interaction. Thus, and here's component 1, one hopes to obtain knowledge of the nuclear forces. So we need to understand the forces by which nucleons interact inside of a nucleus to give us the properties. Then if the forces are known, one should in principle be able to calculate deductively the properties of individual nuclei. So that's step 2. You start with your forces and you calculate properties of nuclei. And that's essentially it. And she says here that only after this has been accomplished can one say that one completely understands nuclear structure. And so this is what hasn't been possible until really the past decade or so. And then she contrasts it with the approach of the models, which I talked about, which are not useless or anything, right? They can give us a clue to the structure of the nucleus, but they require data as input, which then they then use to predict. So this isn't that complete understanding. It's a good picture, but it's not the complete understanding. And this is what we're at. So how do we build it? Well, I just essentially told you what it is. This is, in quantum mechanics world, essentially solving the non-relativistic Schrodinger equation for as many nucleons as you have inside the nucleus, which can be anywhere from a couple to a couple hundred. But again, how do we deal with these two inputs that we need? First is the Hamiltonian. So may or may not know, but what ultimately governs the forces inside of a nucleus is the fundamental theory of strong interactions, which is QCD. But as of yet, we don't have a rigorous way to connect this high energy quarks and gluons to the low energy world of an atomic nucleus. And in some senses, we don't really want that because it's, you don't want to make your life too complicated. So what we have instead is as a low energy expansion of QCD. So we forget that quarks and gluons exist, and our world becomes simply protons, neutrons, and pions, which mediate this force. And so what we can then do is write down all possible diagrams, and with a consistent way of sort of determining which are more important than the others, we have this sort of an expansion. And so you see that 2, 3, and higher body forces arise naturally, and this is complications that we have to deal with within nuclear theory all the time, but we can handle it. Electroweak physics, which is of course important for beta decays and double beta decays and WIMP nucleus scattering, things like this, are also included consistently in this theory. And what you might guess is if this is a perturbative theory, which in principle it is, if this expansion is done properly, we can estimate the physics that's being neglected when we truncate as some given order. So it in principle gives us the potential to assign uncertainties to nuclear forces. And that's what we want. Okay, so I'm going to refer to different interactions a little bit, but just know that they all come from different ways of dealing with this. And one last thing I have to say is, since we're now in low energy land, where we only have nucleons and pions, no quarks and gluons, any physics that's at some higher energy scale, which is of course could be relevant for the energy scale of a nucleus, it's captured here in what we call these contact terms. So these are essentially delta functions, and in each of these terms, there are undetermined couplings, and these can either be calculated from a more fundamental theory or somehow confronted with data. So this is where sort of the art comes in, is how do we deal with dealing with these contact interactions? But that's where this is a whole field. So step 2, so if we had these interactions, we next need to essentially solve the A body. A means the number of nucleons. That's what we always say. We need to solve this A body Schrodinger equation. So if we had an infinite computer, this would just be the mother of all diagonalizations. But we can't really do that. So we need more clever ways to deal with the many body problem. And there are a number that there are a number that are really quasi-exact, which work well with light nuclei up to say mass 12. But to go beyond that, you need something that's slightly more approximate, but still systematically improvable, non-perturbative, all the good stuff. And so the only thing I really have time to talk about is the approach that we've developed at TRIUMF, and it sort of is an extension of another method. So, and this was really pioneered by my first postdoc at TRIUMF, Ragnar Stroberg, who's now at Notre Dame. He's really one of the leaders in the field. So this was really his nice work. And notice this was only in 2017 when we really started this. So what we do is this method, which is sort of a flow equation, but then it cleverly constructs at the end a unitary transformation for you, which does pretty much exactly what you tell it to do. And so, unitary transformations can shift you to a different picture, different basis, whatever, how you want to think about it, but it preserves the physics. And so the first step that we do is we think of a core. Remember those oxygen 16s, calcium 40s, these doubly magic guys? Well, we can think of those as some core. And if we construct our unitary transformation to decouple all excitations out of that core, once we apply that, this gives us the fully correlated energy. So if we apply that, if there's no approximations, this is the exact energy of the nucleus. So we do have to make some approximations along the way, but in principle, that's how we handle it. But the power of this method comes in is because we can take a second unitary transformation, which decouples a small part of the big Hamiltonian. So a few orbits just above the core. And if we apply that transformation, we map all of this physics into this much smaller space. And if we then undertake this much easier diagonalization, then we would reproduce exactly some subset of eigenvalues of the full system. So what this essentially allows us to do is, with this valence space approach, is attack every nucleus between these two cores. And so most methods had been sort of tailored towards calculating these cores, nothing in between. And so that's really where the power here comes in. And so if you know the nuclear shell model, which you may or may not, but this really allows us to extend this first principles approach to everywhere that the nuclear shell model could calculate, which is a good part of the nuclear chart. And so just to give you a little timeline, this is sort of when I got into the games, a young little naive postdoc. And this is what we could do with this ab initio theory. There were methods that could calculate quite well light nuclei, but oxygen-16 was maybe about the best. Fast forward 6 years. Okay, some progress. We see that we can calculate heavier guys, maybe nickel-56, some other nickels. We could calculate along isotopic chains. And that's what these methods that have been developed were really aiming to do. But then remember, this is 2016. Our approach came along in 2017. And this is what we can do as of just a couple years ago. And this is almost entirely because of this valence space approach. We can attack all of these regions between these pillars here. And so with this, the question becomes, okay, now that we can do all of this, what are we going to do? And so we can attack any number of really fundamental questions in nuclear structure from this first principles perspective. And I don't have time to talk about it at all. We've worked with many experimentalists around the world on dealing with many different types of observables, whether talk about masses or spectroscopy, radii, or ways of decaying. There's a number of amazing stories that have taken place here, really with theory and experimental collaborations, and just to give a sense of the impact that we've had, just in terms of collaborating with experiments. But what's more exciting is some of these milestone results that we might be able to achieve. And remember that I said that pinning down the limits of nuclear existence is one of the fundamental questions in the field. And we don't, in the next 10, 20 years of these next generation facilities are aiming to pin that down. Well, if we can calculate everything, we can calculate where things end. And so this was, again, a very nice study that was led by Professor Stroberg here, just came out a few years ago, where we did that. We calculated everything from helium all the way up to the iron isotopes. Here's just giving a sense of how well we were doing on the RMS deviation from experiment. A few MeV, again, many of these have hundreds and hundreds of MeV energy. So this is pretty good. This is on par with some of these mass models that are really tuned to reproduce this. But if we want to determine the limits of existence, we need to think about separation energies and things like this. And so we really undertook a Bayesian statistical approach to this by comparing with known data. I think it's a whole thing. But we were, in the end, able to assign a statistical probability that any nucleus in this entire region was bound or unbound, which means exists or doesn't exist. So the blue are the ones that are well bound. These are kind of along that energy valley that I showed you. Red is sort of a toss-up. So when you get to the limits of existence, things could be a coin flip, and it could be a few keV if that energy scale even means anything to you, but that's well within any uncertainty of our approach. So there's going to be some that are just coin flips, and here this is essentially unbound. And so if you follow where this drip line is known up this neutron deficient side, well, you see that we're agreeing within any sort of statistical expectations, and same down here. So this is really now what we hope to be a reliable, meaningful ab initio guide as these next generation facilities attempt to measure this. So this is really where things stood a few years ago, roughly 2022. We could have calculated all this, we haven't done all of it. So this is the sort of potential of what we could do. But we quickly hit a limit in terms of going to heavier nuclei, because remember I mentioned these three body forces. Well, if you have a lot of nucleons and you want to have all the three body forces between them in very large single particle spaces, this quickly becomes intractable. This can be on the order of terabytes, 10, 100 terabytes worth of data. And there's no computer in the world that has that much memory. I wish. But so that was our limitation. And this becomes so enticing when you consider that just above tin 132 here, there's all of these exciting nuclei for double beta decay, for searches for dark matter detection or symmetry violation, which would be just out of reach. We could hit a few of the double beta decay ones, which was good, and we did, but this is the region that we really want to go. Turns out, when you have amazing postdocs, amazing things happen. So it's another postdoc at TRIUMF, Takayuki Miyagi, who has now just started a professor position in Japan, In fact, he's the only professor in Japan now pursuing this type of work, and so hopefully he's the first of many. But he realized that you don't necessarily need all of these matrix elements to capture the physics in our approach. And so forget about tin 132. Let's just go for the star. Let's just go for the heaviest doubly magic nucleus that we know of, lead 208. So we have a way of parameterizing the way that we capture these three bonded force matrix elements. Don't worry, just know that 18 was our previous limit, which if we're looking at lead, that's here. So if you're going to say, is this converged or not? I mean, right? And so, but what he, with his way of restructuring how we store and deal with these matrix elements, he was able to reduce the storage needs by 2 orders of magnitude, which again, it will take you all the way up here, which is fine. But in terms of lead, it means that we can converge even lead 208. So just consider this for a second. This is essentially solving the Schrodinger equation for 200 nucleons and change. And it's fairly straightforward at this point. And just to give a sense of the dramatic progress, so we sort of plot the total number of nucleons that we can handle as a function of the log of the top 5. So basically the computing power. And if this advance were just due to computing, this would be a slow linear increase. And so just to give a sense, it took 16 years to go from oxygen 16 to nickel 56. So 40 more particles. In just 6, we added another 150, and now we're all the way at lead 208. And so this has been, again, a very nice advance. But again, is what do we want to do with it? So we didn't want to just plant a flag. We wanted to make a meaningful ab initio statement from our community. So we joined with some groups around the world to really undertake this study. And it turns out that when you have more neutrons than protons inside of a nucleus, you get this funny thing that happens. And it's what we call a neutron skin. So it forms on the outside of the nucleus. And if you can measure this or calculate it, it turns out that it's connected with parameters in what we call the nuclear equation of state, which is what governs the properties of neutron stars. So if in principle, we could calculate lead 208, the neutron skin, we could then potentially impact the properties, our understanding of neutron stars. So going all the way from these forces to neutron stars. And it turned out, before we published this, there was an experiment done at JLab, Jefferson Lab in the US, which through parity violating electron scattering, yeah, complicated, but they could extract this neutron skin. So we wanted to have a theory statement that would go along with this. And it's actually quite complicated what we did. There's a lot that goes into this because we didn't want to take just 1 or 2 starting parameterization sort of these nuclear interactions. And so we worked with our friends who are experts in machine learning in Europe and in the US. And so they had this sophisticated approach where you, through training on particular data, you could essentially then develop an emulator. And this emulator allows you to do billions of calculations that would normally take hundreds of years in a few seconds on your laptop. So what we're able to do with this is now look at the sensitivity of any particular observable to the fundamental forces, to properties of the fundamental forces. And so what they did was this process of history matching was actually used in some looking for oil wells or something. I don't even know what it is, but it works. And so you could quite easily do billions of calculations looking at the sensitivity to the underlying parameters. And from these billions, through sort of some process where you look at how well they're reproducing some light data, you can say this guy's implausible, this guy's implausible, this guy's implausible. And at the end of billions, we came up with 34 that were not implausible. So these all did well in describing properties of light nuclei. We can then sort of calibrate them, or this process which we call importance resampling, because just because they do well in one region, they're not necessarily going to do well in another. So you can then statistically weight them in sort of a heavier region here. We went from light region to calcium, and then look at what happens when you go all the way to lead 208. And here's sort of their predictions, and the few pieces of data that we wanted to compare to, they did quite well. And so from this, you can have a true posterior predictive distribution in the Bayesian sense of this neutron skin. And so this is our prediction, and this was that new measurement that came out. It turns out ours was actually a little more consistent with previous extractions, but this is what it was. But then we could even go again, like I said, further and compare and look to see from these 34 interactions if there were these correlations that we might expect with these parameters in the nuclear equation state. Don't worry about it here. And so you can just see that looking at the correlation of the neutron skin with these two guys, that there's a very clear correlation. And this is the first time we saw this from this first principles perspective. So really all the way from forces to the heaviest nuclei to stars here in this very nice study. So now we can recalibrate. So remember, just in 2016, we could only handle a few of this. And now here we are as a field. And so what's most exciting to me is all of these candidates here. So the candidates for neutrinoless double beta decay or dark matter detection or symmetry violation, virtually all of them are within reach of our approach. So again, there's many that we're working on all of these, but the one that I would really like to focus on, because it's kind of the most advanced and also quite exciting, is this neutrinoless double beta decay. But now remember that question about this quenching of that GA. Well, it turns out whenever you would go to a double beta decay conference, every talk would be, okay, is GA quenched? Is GA quenched? Is GA quenched? So if we can't answer that question from a single beta decay perspective, we would never be able to from a double beta decay. So again, remember, it's where we never get it right. We're always off by this common factor. And can we do better now in this new approach that I'm telling you? So there's two levels of physics that were essentially missing in this previous part of this story. And so that was treating correlations adequately, the strong nuclear correlations, sort of mediated by this beta decay operator, and also what we call two-body currents. Because I told you that this guy was just essentially a spin flip and changing proton to a neutron. Well, it turns out the weak force can couple to two nucleons instead. So you could have things like this, where it couples to two nuclei mediated by the pion or a contact thing. And these had never been considered in a calculation before. So what we did is we joined up again with groups across the world who had calculated these sort of for the first time consistently with the nuclear forces. Other approaches which could handle quasi-exact calculations in the light region, our other friends who could calculate these couple guys, and then our approach, this valence space approach, essentially everything in between. And so what we found was that, again, when you didn't include this physics that you knew had to be there, you found this standard quenching. So whether we're in a region between oxygen and calcium or calcium and nickel here, we needed 0.8 or 0.75, so the standard quenching. But when we included all of the physics that we knew had to be there consistently in this first principles approach, we essentially solved this problem. I mean, it's not perfect, but it's not a perfect calculation. So what this means is that now GA quenching is not a thing as long as you include all of the relevant physics. And so now we can move to double beta decay, and as long as we know we're including all relevant physics, we should be okay. And so now, again, a number of my postdocs and students have played a key role in this, and I have to highlight Antoine Belly. He's an amazing PhD student. You'll be hearing a lot from him, originally from Quebec, now just finishing his PhD. And so what's the story here? So remember those bands that I showed you on that plot way back? That comes from these gray areas here. But since those were made, there's been a few more sort of quasi-model calculations, which essentially would extend this uncertainty, now not a factor of 2 or 3, but a factor of 6 or even more. So this translates into bigger bars on that exclusion plot. And it turns out several years ago, a key discovery was made by our friends at the Institute for Nuclear Theory and around the US, that when you do a proper analysis of this double beta decay, it's a little bit of a theory, few sentences. In order to properly renormalize this, you need to move a term from lower order to high order, which means that there was this term, short range term, a contact term, which had never been implemented in any double beta decay calculation before because we didn't knew it existed. And when something's at leading order, that means it's important. So all of those calculations I showed before were missing this key ingredient. And in fact, everybody was. And it was actually quite an accomplishment because there was nothing that a priori told you what the strength of this was, which is a huge problem. But these guys are super clever and they came up with it in a later paper, how to constrain this to within some reasonable uncertainty, 30% or so. So now the problem is you can only really include this consistently with the sort of ab initio approach, because this has to be treated consistently with your input forces. But in these models, you don't have that. But still, there are ways that you can estimate how you include it. And this is now what the picture looks like with models when you try to include this term. So now we're looking at factors of up to 10 uncertainty, depending on the isotope that you're looking at. And things are just getting worse. So can we reassess this with our first principles approach? So step one, always compare with somebody who can do a better job than you. So that's what we do, even if this isn't, if we're just looking at light systems, all of the relevant systems are, you know, germaniums and xenons, but you can sort of play a game and compare and see how well you're doing here. And so everything works well there, you know, when we expect it to. And then you can go and calculate all of them. Because remember, as with this advanced where we can move to heavy nuclei, that turns out there are 3 different operators in the standard double beta decay, and that's these top three panels. And then this is this short range contact as well. So we can quite straightforwardly include this in our calculations. And so what you see is this gray. This was our previous limitation with being able to store 3 body force matrix elements. So if this was still our limitation, there's no way we would be able to claim anything near convergence for these guys. So what you want to see is these things level off. And as we go from lighter to darker, everything doesn't change. And once things don't change, you can say you converge and life is great. And so we can sort of even estimate these, any sort of extrapolation uncertainties. And so that's what we have. And so now we can put our results on this other plot. And what might be most striking about this is, in some sense, what you don't see. Because our results here are this red band. So yeah, let's take let's take germanium here as an example. So this is the spread in our ab initio results. It's not a true statistical uncertainty. I'll get to that later. But yeah, as you look across the relevant isotopes, that we're significantly reducing the uncertainties on this. And we also see that our predictions are much lower than what's often seen, which means, you know, it's not great if you're doing the experiment, but at least we know what it is. And the other thing to look at is if you go to the lightest candidate, which isn't experimentally relevant, but it's relevant because many different approaches can handle it. And here we all agree within uncertainties, which is what you would hope to see from this first principles perspective. So yeah, this guy is with nature and hopefully with some nice touch-ups, we can get that through. So it's quite exciting. So we want to go further. This is just being able to do a calculation is great, and it's a breakthrough, but can we learn more? And so what we also like to do in the field is look for correlations, because this matrix element is something we have no idea what it is other than calculations. So if we can find a correlation of it with another something, and even better, something that we can observe, then that can help us even further pin down this matrix element. But the problem is when you go and look, so we use these 34 interactions, and we look for correlations. This is in germanium, between the matrix element and any other number of observables, and nothing looks to be correlated. Not energies, not a radius, except this thing here. And this is what we call double Gamow-Teller. And so this is sort of the strong interaction equivalent of it. And it's attempting, there are experiments that are out there that are, you know, proposing to be able to measure this. And if they do measure it, it will be a nice breakthrough because it will give us some handle on the matrix element. But as of yet, this hasn't been observed. So what do we do? Well, this is where the power of machine learning and great students and postdocs comes in. Because again, this Antoine, with an undergrad that I had, who was an expert in sort of AI and machine learning, really developed our own emulator. So again, you have to train it on some data, but after that, it can give you billions of calculations in, you know, a few minutes. And so what we were able to do then is just say, looking at an energy. So the energy of germanium-76, this just sort of shows how well our predictions do compared to being trained. But what you can do is then look at the sensitivity of the underlying parameters of your nuclear forces. So we're really connecting this energy to the underlying forces, like parts of the underlying forces. And we see that there's a spread. And this was complementary with what a few other groups had done that also had emulators. But nobody had looked at double beta decay before. And when we did that, this was striking. We see that the nuclear matrix element is sensitive to one term in your fundamental forces, just one. A few here, but and that's essentially it. And when you look at what it is, C1 as 0, I don't know, actually, 1 as 0 sounds like these things. So for decades, they've been measuring nucleon-nucleon scattering. And from scattering, they measure cross-section. And from cross-section, you extract what you call a phase shift. And so these phase shifts depend on your combinations of angular momentum and stuff. And the easiest one that you ever come across is the 1 as 0 phase shift. So there's a whole lot of data out there on this phase shift. So if we now can take these 34 interactions and look at how the double beta decay matrix element correlates with this observed quantity, this phase shift. So the phase shifts is at different energies, right? You're colliding two nucleons. It can be at low energy or high energy. So there's no correlation whatsoever if we're at low energies. But by the time we get to 50, 100, 200 MeV, there's a very clear correlation. In fact, you can see it maybe better in this type of a plot. So by the time we're at 50 or so MeV, we have a clear correlation between the double beta decay matrix element and something that's observed. So we can add a new panel here where we now have an observation. This is the first time that we've had anything like this. But even better, now we know that as long as an interaction is going to do well in reproducing phase shifts, it should be more statistically meaningful. So if we go back and try to do a pure true Bayesian statistical uncertainty analysis of the matrix element in, say, germanium 76, which we did, going to be in PRL fairly soon. Rather than starting from 34, now we talked to our friends and they gave us 8,000 or so of these different interactions and change. And so what we could do was we could statistically weight them by how well they reproduce this phase shift, looked at all of the different possible sources of error in the full chain of this calculation, whether we're talking about errors from the underlying force, from our many-body method, from how we're calculating the double beta decay operator itself. And in the end, we were able to construct, again, a true posterior predictive distribution for the matrix element in germanium 76. And the only reason we weren't able to do the other ones, the heavier ones, is because nobody else can calculate those yet. So once somebody else can, or once we can estimate our many body parts better, then we can do a similar analysis. And so one thing to note here is that the mean value here, these little points that are scattered, these are the same ones that went into our previous analysis from those bands. And we see that since they reproduce the phase shift, they're doing extremely well already. So if we can now take this and put it on the plot, we have a true now, again, 68% confidence interval here for this matrix element. And we see that it lines up almost perfectly with what was already on this plot. So chances are, as we go to the heavier cases here, that these are not going to be so different than if we do an independent statistical analysis. So that gives us a lot more confidence in these heavier predictions as well. And so why is that important? Well, when we go to what's coming out of these searches, right? So this is how things looked sort of at the end of the previous generation of these searches for double beta decay. There had been some claims by some experiments to have begun to probe this inverted hierarchy of neutrino masses, again, given some choice selection of matrix elements. But if you look at ours, and it's really just this lower band with the hashed, this is our predictions. And it looks like there's probably no way that any group or any experiment has probed this yet. So we wouldn't be surprised that there hasn't been an observation yet. But with the next generation of these experiments, they have projected sensitivities for what they'll accomplish over the next 10 or 15 years. And these are kind of the key leading players. We call them Legend, Cupid, Snow Plus here in Canada, and Nexo, which will probably also be here in Canada. And looking at their sensitivities for what they might probe over their lifetimes. And it looks like indeed, most of them will probe most of this inverted hierarchy. But what's more striking here is that compared to these other models, we reduce this uncertainty by well over an order of magnitude. So this is exactly what all the people building these types of experiments would love to see. And well, here it is. Okay, so that is where sort of the first chapter of our first act ends. There's a lot more to do on double beta decay. I don't want to give a sense that we're just done and moving on. There's a lot more exciting things we can do. But I just want to give a hint of where we can also go. A lot of these other exciting areas for searches for new physics or understanding the universe. And the first thing is, since we can go to this region all the way up here, we know that this is very important for understanding how the elements are formed in the universe. So this process that we call the R process, the rapid neutron capture process, which takes place in neutron star mergers or maybe a little bit in supernova explosions, but it's how we generate elements above iron. Because in stars, that's as far as you can burn. Beyond that, these elements have to come from somewhere. And so it's a big puzzle. And so people like my collaborator at TRIUMF, Nicole Vash, and her PhD student are experts on really these sorts of simulations. But to run these simulations, you need input. You need you need data, you need masses, you need capture rates, you need all these things. And especially in this region, only very little is known. And even beyond that, very little will be met. Well, a fair amount will be measured, but not enough will be measured in these next generation rare isotope beam facilities. But with our calculations, we can go all the way down here, all the way to the drip line. And so, yeah, this is important for this, what we call the third R process abundance peak. And just to show that we've already done these calculations all the way from lead down to, I guess this is tin, 180, I don't know, whatever this is, but all the way to where the limits of existence are. And so this is what you need to know as input to these R process simulations. And there's a plot coming soon because they've already showed how this affects their abundance predictions, but it was basically a screenshot of a plot on a computer, and I'm not going to subject you to that, but coming very soon. Again, I mentioned searches for dark matter detection. So the way we hope to potentially detect dark matter is through a WIMP or something, recoiling off a nucleus, and we're there to observe it. There's also a process called coherent elastic neutrino nucleus scattering, where you kind of sort of have a neutrino come in and he bumps a nucleus and it goes out, but then there's sort of these recoils. And this is also very well given by the standard model. But so any deviations from the standard model prediction will give you hints about new physics. But in order to, again, accurately interpret that, there are, in both cases, there are these theoretical quantities which we need to calculate from the underlying theory. And again, this is something that we've done. This is for dark matter detection. This is for all the candidates for this neutrino scattering as well. So making progress on a number of nice directions. But this is perhaps the one that I'm most excited about. And again, it's my PhD student is now going to, as a postdoc, to MIT to work with this student at MIT on these symmetry violation searches. So we exist. We're here. There is an abundance of matter over antimatter in the universe. And in order for that to happen, as far as we know, symmetries have to be broken in our universe. And the source of that is a complete mystery. But there are these searches for CP or time reversal violation, the same thing, that have been ongoing for decades. In fact, it even started in before 1960 for what we call searches for these EDMs, electric dipole moments in neutrons. And this has really been progressing for decades and decades. You might be familiar with this fantastic experiment that's done at the University of Washington, looking for symmetry violation in the mercury molecule. That's still sort of the world-leading experiment. But so this is sort of where things look to be sort of trailing off in a way. And there's this tremendous discovery. So just to show you what this is, so when you have a violation of symmetry, there has to be a new particle that would be mediating this. And you can sort of connect you can connect the observations here to what the mass of that particle might be. And so here's the current LHC limit. So you see, even now today, we're probing new particles beyond what the LHC can. But there's this tremendous discovery window between where we have here that's several orders of magnitude, 3 or 4 orders of magnitude, to where we have known low-level CP violation in the standard model. But it turns out that when you look at what are the most favorable systems, there's this beta 3. And this means octopole deformed, a nucleus. And this is much more sensitive than something that's more spherical or whatever. And in fact, there was one of these nuclei was discovered several years ago. Of course, it's on the cover of Nature because it's so important for searches like this. So this will get you a lot. But what is absolutely fascinating is you can look for you can search for symmetry violation now in molecules. And so something very fascinating happens inside molecules. So normally you have to apply an strong electric field, and this would be your typical radium or whatever. But inside of a molecule, if you have a polar molecule, the fields that this guy would feel inside of the molecule are orders of magnitude more than what you could ever generate in a lab. So much more that the enhancements are on the order of over 1,000. So that is ridiculous. And again, of course, if a new discovery were to be made, we need reliable nuclear theory in order to begin to extract what the source of the symmetry violation would be. And just to show you what molecules might get you here in the next, say, 10 or 20 years, this is where we would go. We could potentially probe 1,000 TeV masses for new particles with these types of searches. This is ridiculous. The fact that you could, this is just never seen in physics. And just to give you a sense, I was just thinking about this. What if we had the same improvement in our searches for double beta decay? Well, we would go all the way down here. In 10, 20 years, we're hoping to maybe get here. So that's how ridiculous the enhancements are in these molecules. And to date, there's really, like I said, no good theory for this. So, so it's very exciting to be part of this because we're now just starting to be able to calculate these. Here we have calculations even for these radium nuclei, which are the best known targets as of today, and will be used in many of these experiments. And where I just want to end now is in searches for other symmetry violations. So we know that the weak interaction violates parity, right? We got Nobel Prizes back in the 50s and 60s for this. But what about parity violation inside of a nucleus? So if you can start to measure parity violating properties in a nucleus, what this means is you're probing the weak structure of the nucleus, which is something that we don't even think about. Like, what is the weak structure of the nucleus? But we can start to do that. And so there are these moments. Okay, I guess you could sort of think of it as sort of the W and Z exchange between nucleons inside of a nucleus generates these sort of toroidal currents, which we call anapole moments. And again, you can search for these using these laser techniques. And in molecules, you can go even further because there's an energy denominator here that's tunable. So you can really go to like essentially making this zero. So we can have on the order of 10 to the 10, 10 to the 11 enhancements in these searches. So this has never been discovered, but it will for sure be discovered by my friends doing these sorts of experiments in really the next 5-ish or more, probably about 5 years. They're quite confident. And there's only been one measurement of this ever, and it's never been repeated. This was back in the late 90s by Carl Wyman's group. So, you know, they're not exactly low-level players here because it's so difficult. But this will probably be routine because of what you can generate inside of a molecule. And this is, again, something that we started to calculate. This is in a light nucleus, just a sort of benchmark, but we're even recalculating this guy as we speak. So a lot of exciting potential for new physics. Yes, there's also the super loud, which lets you get at the up-down element of the CKM matrix. Just sort of flash this. This is, again, something we can calculate, but things aren't terribly well converged, but I have a nice new student who's coming in this summer, and hopefully we'll change that, and we can make an impact there as well. So, and okay, also we can do atoms. You think about doing molecules and putting these things on supercomputers. So if there's any sense that I want to give you here is that all of this, as cool as it's been with the double beta decay, it's really just starting. There's so many new avenues where they're talking about just even simply nuclear structure, but all of these exciting connections to beyond standard model physics. Yeah, if you're at all interested here or out there in Canada land, yeah, join our revolution. Like, join this amazing group of people who've made it happen across many different areas, and a lot of them have gone on to amazing places: MIT, Princeton, Perimeter. Yeah, join the club, and I'm happy to take questions. Thank you.
Thank you for a very interesting and inspiring talk. When you showed the nuclear matrix elements, they do not scale with mass or proton number in a simple way. And maybe that's expected because the system is so complicated. But in your model where you have this core and you have this shell structure above the core, could you expect to have a simple structure scaling properties as a function of distance to the core when you go away from the magic numbers?
Distance from the core.
I mean distance in terms of proton number or nuclear number.
No. In fact, so that's the beautiful thing about this approach. That's sort of how you would think of it in the standard shell model picture, is you have a core and then you have sort of one interaction that governs that whole region, and you add more and more nucleons. But we don't do that. We generate a valence space specific for every nucleus because you want to make sure that you're capturing the 3-body forces between all of the valence nucleons. And so this is, of course, nucleus dependent. So in principle, this works just as well for nuclei near one end of the shell as at the other. So we have several in the first paper there, the 2017, we show how well it does across, as you move away from the core. And it's, at worst, you get like a slight 1% deviation by the time you get to the very, very end or something. But it's, that's why it works so well, is because it treats all of these essentially on an equal footing and with all of the known physics there. So
Thank
yeah.
you.
Sure.
Questions?
So that was ways back, but
Sure.
you showed a plot where you made predictions at least of what will exist for some of these nucleons, sort of, relatively heavy for what you
Yes.
have. I don't know if we can go back to that slide. It might take forever
Okay.
to find. It's like
Could
somewhere
be.
in the middle.
Whoops.
I guess the status of that is what you're just sort of waiting for the facilities, these next generation ones, are going to get there and
Okay.
hopefully.
Oh yeah, for the drip line maybe. or-
I think it was actually not
This
that.
one?
There we go. Yes, yeah, actually,
Yeah,
yes,
okay.
it was that one. Yes.
So right. So these are our predictions.
Yeah.
So the filled in circle is where the known limit.
Mhm.
The open circle is the last observed one. So nothing's been observed past this open drop. So we predict that for most of these, there will be at least one or two more that will be observed.
Now this is weird, right? Because how exactly do you put an uncertainty on a binary, exists or not?
Oh no. We put a probability for it to be bound or not.
You put a
So-
probability. Okay.
Yeah. So we can,
So-
yeah, this is, I can show you all the details that go in
So
there.
it wouldn't be
it's-
like an error bar, but it would be like those probability distributions you sort of showed that you assigned to those error bars later on. Okay.
Yeah. So right. So for every nucleus, it's, for this one is 100%. This one is maybe like 12%, something like that. But yeah, but that was through this whole, again, we did a whole Bayesian analysis of this, and for everyone, you're able to, assign a distribution for whether it's bound or unbound. And so that's, because in some sense it's, because these energy, it could be a matter of a few key for whether something exists or doesn't. And for us, that's essentially meaningless. We'll never get that level of precision. So it made more sense to think about this question probabilistically. So, so that's kind of what we have here. And so you can see for calcium, who knows? It could be any of these could exist or they could not. So it's, but this is a particular area where they're quite interested in measuring. But yeah, and happy to answer another one if you.
Trying to think. I kind of had another one, and mostly Reiner answered that one. But
Okay. Don't be shy.
Any more questions?
Okay.
Okay.
Thank you. I won't say I caught everything you said,
Fair enough.
but
It
at
was a
the
lot.
at the end of the day, what it looks like is you've improved a technique and it makes better predictions than the old predictions. And you don't really need to introduce any new physics to understand observations of nuclei.
Yeah, in principle, you should, like from the quote, you should be able to understand the nucleus if you just know the forces and you can solve the many-body problem.
And that's what I'm sort of seeing here, right?
Yes, that's exactly. These have all been calculated in that way.
So
Yeah.
then the question
Everything I
is,
showed was like,
the question is, are there places where that's not true?
there are places where it's not true yet. Because if you go, let's see where's my.
Yeah, you're going through all your examples and kind of saying,
Yeah.
hey, if I use my technique,
But-
I get the right answer.
Oh yeah, but even then, whoops, this is. Oh, okay. I don't know what's going on here. But where I showed where you could go past lead, like anything past lead at this point, we can't do. So we have to still rely on the models there. And you saw there's the region between the blue
Yeah,
bands. So that is again. So our limitation is you at least need to be somewhat close to one of these closed shells, because in those intermediate regions, nuclei become very deformed. So
Yep.
this works well starting from sort of a spherical picture. If you want to do those, you can start from a deformed starting point, but that's much more computationally difficult. So that's been developed in the field. Which I should say, even
But-
the germanium.
But if I go back to your quote from, I
Yes.
can't remember the name of the lady,
We're go.
where she said, if you understand the forces, you
Yes.
can then understand the nuclei.
I see.
You're 2/3 of the way through completing that statement, as you might say, where you've got this part done.
Oh no.
You can't quite do the part above it yet.
For everything that I showed, we did. There's the only limitation is really being able to apply these methods. But there's
Exactly.
nothing missing in the method necessarily. It's just some nuclei are more difficult to apply it in than others.
Yeah,
So,
and I
so
don't
yeah.
want to take that away from you
Yeah,
at
yeah.
all.
so that's why these regions where they're more deformed, Yeah, deformation is just something that's very tricky. But our friends in the US are really developing a nice way of handling that. So that might not even be an obstacle at a certain point.
Nice, neat
In
stuff.
the near future. So it's, yeah. So we can't do everything, but sort of where that was all highlighted in blue is where this approach essentially would work. And we should be able to handle any nucleus in there from this sort of fundamental picture. Yeah.
Okay, thank you very much. Jason, unfortunately, I have to stop because we are really over the allocated time. I see from organizer that they are hinting that it's time to
wrap up.
move on. And of course, we would certainly thank once again Jason for giving us a very detailed report on advances in TRIUMF. It's amazing the stuff that they are doing. Now, I think, well, let's just first, hello, thank you very much.
Thank you.
Let me say, on behalf of CAP, thank you everybody for participating in this series all the year. And for our students, you do have opportunity to go through all other 5 presentations and through Jason, which will be posted pretty soon. So we thank everybody involved in this. And of course, we appreciate CAP efforts in organizing these tours across the country. It is quite an activity for all of them involved. We thank them and thank you everybody for coming today. Thank you and all the best.
As I said before, I am Gwen Grenier, National Coordinator for the 2024 CAP Lecture Tour Series. At this time, I'd like to thank the staff in the CAP office, the University Coordinator, and our host, Prof. Sasha Kustav, for helping to organize today's talk. Thank you also to Prof. Jason Holt for an excellent presentation, and thank you all for participating. I also want to thank the CAP Foundation and its generous donor who provided an endowment that has made the CAP Lecture Tour possible. Please consider making a charitable donation to the CAP Foundation today to support its many other significant programs supporting scholarships, prize exams, resource development, and other activities promoting physics to students. This is the last stop for the 2024 CAP Lecture Tour, and I'd like to take this opportunity to once again thank all the CAP regional coordinators, speakers, host departments for providing an excellent series of lectures this year. And a huge thanks to Ellen Malloy in the CAP office, without whom none of this would have been possible. Ellen has worked closely with me all year round and has really run the entire lecture tour behind the scenes almost single-handedly. As a reminder, all participating students, both online and in person, are invited to remain to have informal discussions with Prof. Holt, and online participants may now unmute themselves and turn on their videos. So have a great day. Thank you very much.